Alright, so I've got up here the where we left off last time, and we're solving the system of equations. Right, and the way we do that is we find the trace, the determinant, and then compute the characteristic equation. And that gives us our eigenvalues lambda. And then for each lambda, we plug it back into our system of equations, and we solve for the eigenvector v. And so we found that there are two cases so far. If lambda has distinct real values, in other words, if the discriminant is positive here, then we have two real eigenvalues and two real eigenvectors, and we can formulate the solution by taking a linear combination of these. C1e to the lambda 1t v1 plus C2e to the lambda 2t v2. Good. If lambda is complex, then we really just need one eigenvalue and one eigenvector, and then we have to compute e to the lambda t times v. And then the real part and the imaginary part are the two pieces to the solution. And that's really just like chapter 3, when we took the real part of e to the lambda t and the imaginary part of e to the lambda t as our two solutions to form a fundamental set. Okay, and so again, in this case then we would take C1 times the real part of e to the lambda t plus C2 times the imaginary part. And that brings us to the third case, which is the topic for today, case 3. One real eigenvalue. And so it's going to be doubled up. Now actually there are two cases I want you to think about. Consider the difference between 1, 0, 0, 1 versus 1, 1, 0, 1. Okay, I'll say in both cases that lambda equals 1 and 1. But there's a really big difference between the two matrices. In this case, if we're looking for v1 and v2, in this first case, we would have our 1 minus 1 times v1 plus 0 v2 equals 0, and then 0 v1 plus 1 minus 1 v2 equals 0. That just means that 0 equals 0. And so therefore v1 and v2 are both free. And so you can pick any v's for this to work. So one way to do that would be to take like v1 to be 1, 0 and v2 to be 0, 1. And then in this case, this is the really special case where you have two eigenvectors and two eigenvalues. Well, you have a double eigenvalue, but then you have two eigenvectors. Because in this case, you could say C1e to the lambda 1t v1 plus C2e to the lambda 2t v2 is your solution set. Okay, so this, I should say, is really a rare case. Rare. That doesn't happen very often. This is really the case the second case is really the one that you run into more often. And so I should say, just as a summary for this first case, that if you have two free eigenvalues or two free eigenvectors like this, v1 and v2, then go to case 1. So this is really case 1. Okay, so we're going to assume that that case does not hold, and so look at this case when we put in our values here, 1 minus 1 v1 plus plus 1 v2 now equals 0, and then 0 v1 plus 1 minus 1 v2 equals 0. And so we are left with a condition that v2 is equal to 0. Right? And so v1 can be anything, and so we write our vector as like 1, 0. Okay, so this is the problem. I've only got one eigenvector, but two eigenvalues. So what am I going to do? I need another eigenvector somehow. Well, there's a couple ways to write the solution for what we're about to do. So I don't like to do it this way, but I'm going to just tell you what the answer is. And then we're going to check that it works. And so here's how to work this. So given x prime equals ax plus by, y prime equals cx plus dy. I guess that's okay. Usually, I guess we've been switching x1 and x2 in there. Okay, and then we have lambda is a double root. I should say I need an IVP. We'll say x of 0 is x0 and y of 0 equals y0. Okay, then the solution is x of t is equal to e to the lambda t, that's your sole eigenvalue. Then we're going to have x0, this is your initial condition, plus t times w, where w satisfies something like eigenvector. It's a minus lambda x0 plus by0 equals w1, and then cx0 plus d minus lambda y0 equals w2. This is kind of an odd equation, but it looks very much like the eigenvector equation. It's just there's some subtle differences here. This is going to be called w is called a generalized eigenvector, but you don't need to know that. It's not quite an eigenvector because that's not the eigenvector equation, but it's similar. And so let's see how this is going to work in practice, because in practice I think this goes pretty easily. So let's just try one out. Let's try x prime is equal to 2302 times x. Okay, and so now our trace is 4, determinant is 4 minus 0, so 4. So that's lambda squared minus 4 lambda plus 4 equals 0. And so that's lambda minus 2 squared equals 0, or lambda equals 2 and 2. Okay, now if we set up our eigenvector equation, that would be 2 minus 2 v1 plus 3v2 equals 0, or 0 v1 plus 2 minus 2 v2 equals 0. So we just have v2 equals 0. And so you could probably stop here, because this means that you only have one eigenvector, which is of the form 1, 0, and we're actually not going to even use that. However, this equation we are going to use, it's going to be 2 minus 2 x0 plus 3 y0 equals w1, and then 0 x0 plus 2 minus 2 y0 equals w2. And so what does that say? That says 3y0 equals, oh gosh darn it, 3y0 equals w1, and what's the second equation say? 0, 0, w2 equals 0. Good. Now, you can choose any w1 and w2 that satisfies this relationship. In this case, we'll just pick it, 3y0 and 0. And so now we have our solution. Let me pull this down so you can see. So our solution is x of t is equal to e to the 2t times our x0, y0 plus t times 3y0 and 0. Good. Now, just so you don't think this was a fluke, I wonder if you can show that this is indeed the solution. show this satisfies the DE. Ah, you're saved by the bell. I see we're at 10 o'clock, or at 10 o'clock, 10 minutes. So we'll be back in the next video to show how this satisfies the differential equation. See you then.